Hello everyone, my name is Uma Mahesh Reddy Ipala and I am a graduate student at the University of Florida. This presentation is for the Image Processing and Computer Vision course, and the topic of this presentation is face detection using Viola-Jones algorithm. First things first, what exactly is face detection? Given an image, if the tool or the software that we use is able to identify whether a human face is present in that image or not, then that process is called face detection. Now that's only one part of the definition. The second part of the definition is about finding the location and size of each and every human face present in that image. In short, face detection can be classified as a distinction between an image having a face or not having a face. What is the importance of face detection? Security takes the upper hand. Say for example, surveillance systems and tracking. From the surveillance systems, we are able to get the footage of a person that we need to identify. And tracking is the face detection technique that we're actually able to identify who that particular person is. Next is the automatic face recognition systems, like the ones that are being used in many laptops, wherein after being switched on, they are able to scan the face of the user before they are able to proceed. Finally, the interaction between man and machine, such as the artificial intelligence, wherein it is actually able to detect the face of the user or the person it is communicating with. And in fact, face detection is the starting point for the interaction between man and machine. Face recognition. This is one area that generally people confuse face detection with. Now, what exactly is face recognition? Face recognition can be defined as the process of identifying a previously detected face and classifying it into either a known face or an unknown face. Like the diagram clearly shows, there are three stages before a face can be identified. Now, assuming that there's an image in the face, that's the assumption we take. That's the assumption we make. Now, when that image is fed to the face detection block, it is able to identify that the image has a face. Secondly, now that identified image is passed on to the feature extraction stage, wherein the essential features from the image are taken away and the non-essential features are discarded. By non-essential features, I mean the features that are more or less redundant. Now, if one pixel and the other pixel is different from each other, now I'm talking at pixel level. Now, if one pixel is different from the other, then that particular pixel is stored. Now, if two pixels are the same, then one of them is discarded. Now, after all those features are extracted, it is fed to the face recognition block, and that block is able to identify that image, the person in the image. More about the differences between face detection and recognition. Face detection has only two classifications: face and no face. Whereas when it comes to face recognition, there are multiple classifications. And the reason for this many classifications can arise from the fact that there are a large number of permutations and combinations that take place depending on the face shape, the form of the eyes, nose, mouth. All these factors are taken into consideration, varied, due to which there are a large classification there's a large classification set that is formed, and the face recognition algorithm has to identify one particular face from that classification set. Finally, in a logical sense, face recognition cannot be carried out until face detection is complete, and this is clearly visible from the diagram. Now, going on to the challenges that are faced by face detection processes. Of all the challenges, the three that clearly stand out are feature computation, feature selection, and real timeliness. By feature computation, the first question that comes to our mind is what are the features that have to be computed and how fast do they need to be computed? The faster the better, because as the speed increases, we are able to actually compute more features. Secondly, feature selection. Of the features that are computed, we need to take only those features that are highly essential. Finally, from the extracted features, we have to find out only those areas that actually contain the image, and these are called positive areas. Viola-Jones algorithm is one such algorithm that addresses the previously mentioned issues. It uses something called the integral image representation to solve the problem of feature computation. The ADA boost training algorithm, also called the adaptive boost training algorithm, solves the problem of feature selection, whereas the cascade of classifiers takes care of real timeliness issues. Now, going on to integral image, the first question that is generally asked is, can a simple feature like a value indicate the existence of a face? Generally speaking, uh, each and every face has a set of property, has a particular property. Uh, some of the properties are the eyes region being darker than the upper cheeks, the nose bridge being brighter than that of the eyes, and so on. Now, this information is called the domain knowledge. Domain knowledge is actually a very important concept because it is from this domain knowledge that we get something called the values that was mentioned in the previous slide. Now, from these values, we can find out information such as the location size or the value of a particular feature. By location size, I mean the eyes and the nose bridge region, and by value, I mean how dark or how bright is one part of the face from the other, and so on. Now, coming to rectangular features. Rectangular features are something that are very ideal for the calculation of an integral image. Now, how do we calculate these rectangular features? It is simple. Now, it is the difference between the sum of all the pixels in the black area and the sum of all the pixels in the white area. There are generally three forms of rectangular features. There are two rectangular features, three rectangular features, and four rectangular features. Now, the Viola-Jones algorithm makes use of the two rectangular features form. Now, for example, the difference in brightness between the white and black rectangles over a specific area. That is a two rectangular feature property that is used by the Viola-Jones algorithm. It is clearly visible from the image snippet on the top right of the screen. The top row has a black area and a white area. Now the value of that region, which is called a rectangular feature, is just the difference between the sum of all the pixels in the black area and the sum of all the pixels in the white area. Now since that is a two rectangular feature, Viola-Jones actually makes use of that. Now each and every feature is something that has or is constructed of any size. Uh, the next question is, why are pixels not being considered and why are features being considered? It's simple. because when it comes to feature extraction, we need the output to be as fast as possible. And by making use of feature extraction, it is being shown that it is a faster technique when compared to pixel extraction. And the second reason is that feature extraction contains some domain knowledge, and that domain knowledge is very essential when it comes to the later stages of the algorithm. Now the next step is the image to integral image computation. That is, given an image, we have to convert that image into something called the integral image. Now that is a very simple process. At the bottom of the screen, there is a 3 cross 3 matrix that says input image, and there's another 3 cross 3 image that states that it is an integral image. Now in order to calculate the integral image, we need to make each pixel equal to the entire sum of all the pixels above and to the left of the concerned pixel. Now, say suppose we need to find out the pixel value of the middle matrix region. So that is equal to the sum of all the pixel values on top of it and to the left of it. That is, this value is equal to the sum of 1 plus 1 plus 1 plus 1, so 4. So that's how we get the value of 4 in the integral image. Now this process has to be applied to each and every pixel in the input image, and that can be converted into the integral image. Now the next step is to calculate the integral image representation from any rectangular sum in a constant time. The image at the bottom right is an example that illustrates this function. Now for example, we have to calculate the integral sum inside the rectangle D. That is calculated as the sum of the integral image of point D plus the sum of integral image of point A subtracted from the integral image of point B, and that is subtracted from the integral image at point C. Now this is a general method, and this can be extended to the 2, 3 and 4 rectangular features. And in order to calculate these rectangular features, we need 6, 8 and 9 array references respectively. Now this process is a fairly straightforward process, and the computation time that is required to get this process done is very small rather. Second property is feature selection. The second issue that was previously mentioned is feature selection. Now, what exactly is the main problem plaguing the various feature selection techniques? Simple, there are too many features. Now, consider a sub-window pixel having now consider a sub-window having 24 cross 24 pixels, and within this small region, there are approximately 160,000 features obtained from various combinations of location, scale, orientation, type of features. Now it becomes very impractical to compute all of them. Even though it is possible, it is a computationally expensive process and consumes a lot of time. Now we have to select a subset of all those features that are relevant and informative to model a particular face. Now the hypothesis that is considered by the algorithm, the Viola-Jones algorithm, is that a very small subset of features can be combined to form an effective classifier. Now this hypothesis is the backbone of the ADA boost algorithm, ADA boost algorithm. What does ADA stand for in ADA boost? Adaptive boost. Now what the adaptive boost algorithm does is it constructs a strong classifier which is equal to the linear combination of the weighted simple classifiers. Now the capital F of x represents a strong classifier, or rather the capital F represents a strong classifier and the x represents the input image. Now, alpha 1, alpha 2, alpha 3 are just the weighted products or the weighted scalar units that will be discussed later on, whereas F1, F2, F3 represent the weak classifier. So the strong classifier is actually equal to the sum of the product of the weight and the particular weak classifier. Now going on into the features of weak classifiers, each single rectangular feature can be considered as a simple weak classifier. The adder boost is a very iterative algorithm. Is an iterative algorithm as in it performs a series of trials and every time it selects a new weak classifier. Now say suppose there's a particular example. In order to process that example, by example I mean a sub-window of an image. Now in order to process that sub-window of an image, it it adopts a new classifier for every time that sub-window is being processed. The weights are then applied over the set of example images. So during an iteration, each example or an image receives a weight that determines its importance. Determining its importance is a phrase that is used to refer to being error free, having a very small rate of error. Now, if we are given an input image or example image that are labeled as either positive or negative, a positive image is the one that contains a face, whereas a negative image does not. So initially all weights are set equally. They are at status quo. The algorithm is then repeated p times. The first step being that we need to choose the most effective classifier that will be a component of the final classifier, which what we call the strong classifier. Then the weights are updated to emphasize the example which are incorrectly satisfied. So we know, by doing this we know which weight is more effective, which weight is effective and which weight is not effective. So this makes the next weak classifier to focus on harder set of examples. Now the strong classifier is finally obtained, which is a weighted combination of p weak classifiers, and the weights are according to their accuracy. Now, talking about the adder boost algorithm in a nutshell, the main problem is that in each round, a large set of possible weak classifiers are obtained. But the question here is which classifier do we choose? Because each and every classifier has a single feature. Now, like I previously mentioned, we need to decide which feature is important and which feature is unimportant. So this actually causes an issue because we need to know which classifier we have to choose so that the final image uh, can be easily identified and we do not get a false representation of the image that is being supplied to us. And this is done by choosing the most efficient classifier, that is, the one that best separates the examples. In short, the classifier that has the lowest error. Secondly, the choice of the classifier corresponds to the choice of the feature. This statement indicates that now if there's a particular feature in the image, like say suppose the eyes, that is a very important feature that is needed for a face detection algorithm and that has a very high precedence over the other features like say suppose the cheek or the lesser darker regions below the eyes. Now those are not as highly important as the features that are used to represent the eyes. So the choice of the classifier containing the feature is also an important choice to be made. Finally, the strong classifier is said to consist of T features. In conclusion, The adder boost algorithm searches for a small number of good classifiers, which is called feature selection. We are basically selecting the features that we need, and it adaptively constructs a classifier taking into account the failures of each of the chosen weak classifiers. Then the adder boost is used to then select a small set of features and go on to train a strong classifier. The third and the final problem is solved by the cascade classifier. And the problem that was previously mentioned is the real timeliness problem. Now, there is equal computation time that is being spent on all the sub windows of an image, and on an average only about 0.01% of all the sub windows are positive. That is, one out of every 100 sub windows contains a face. So the 99 sub windows are actually discarded. And thirdly, some amount of time must be spent on the potentially positive sub windows. Some amount of time, meaning some extra time, has to actually be spent on the positive sub windows so that we can identify the faces. Now, when it comes to a simple two feature classifier, a 100% detection rate is obtained and a 50% false positive rate. This is because the classifier 1 acts as the layer that weeds out the negative windows, whereas the second stage of the classifier, or the second layer of the classifier, takes a harder action on the negative windows which actually survived and passed through the first layer. Now, I previously mentioned that a two feature classifier has a 50% FP rate. FP stands for false positive rate. And when it comes to statistics, while performing multiple computations, false positive ratio refers to the probability of incorrectly rejecting a null hypothesis for a particular test. That is, we incorrectly reject a subwindow stating that that particular subwindow has no face image. This false positive rate refers to the expectancy of the false positive ratio. Now, going back to the explanation, a cascade of more complex classifiers achieves even better detection, implying that if a classifier has multiple stages, then the detection rates will improve greatly. Now, going on for the demo. For the demo, I'm using the MATLAB 2015 B version. This is because the Viola-Jones algorithm developed requires a particular object, which is called the Vision Cascade Object Detector, and that is found only in the 2015 B version of MATLAB. Now, the code consists of three parts, which is called the face detection, nose detection, and the mouth detection. Now, I feed it with an input image, and that image is mine, and we get the particular output. Now, going on to run the code. So, figure 3, as it is flashed on the screen, shows the mouth detection. Now we're getting an additional square over here. This is because the object that is being used has a default value of 4. So in order to remove that, the default value has to be manually overwritten. So I'm using this at the default value, and even though we get an extra region showing that might be a potential mouth, it clearly points out the mouth in the image. Nose detection. Similar explanation for why we get three regions But like I have mentioned, once it is overridden and we change the default values to higher numbers, then the unnecessary regions are weeded out. And the nose is clearly visible over here. Finally, the face. The object is so strong that it can actually detect the faces very clearly without adding any additional data like the ones from nose and mouth. So provide any image to this object, it will clearly detect the face. Now going back to the presentation. Now these are the results of the code. So the face, mouth and nose are detected. Now while feeding various images, this is an image that consists of multiple faces, and it is seen that the code does a great job in finding out uh, a majority of all the faces, and only a couple of faces are actually left out. Nose detection. The contrast of this image is not so high, not so good, but still, even though the contrast is bad, the algorithm does a great job in finding out the exact position of the nose. And finally, the mouth. It clearly finds out the position of the mouth for all the three characters that is visible in the picture. Thank you.